move outwards. But it's as I say, for industry, it's not a nice thing to hear. But time has already shown us, we were supposed to have automated driving vehicles on the road a year or two ago, and we haven't got that. So actually, I think certain amount of patience needs to be kept, but we need a systematic approach to getting out of this, the value of tears in the hype cycle.
Thanks.
Thank you so much, Professor Burton.
You're welcome.
So now we'll move on to our paper presentations then. Today we'll have our third session, which is on perception and adversarial attacks. Do we have author of the first paper, Shashank?
Can you hear me?
Yes, perfectly. Do you have a slide you want to share?
Yeah. Can you see the slides?
Yes.
Okay. So, hi everybody. I'm Shashank Kotian, and I'll be talking about our paper, The Deep Neural Network Loses Attention to Adversarial Images. So first, let's talk about what is an adversarial image. An adversarial image is created by a special class of algorithms, which are adversarial attacks. And the objective of these adversarial attacks is to misclassify the neural network. So in the image on the left, the neural network thinks it is a cat, which is true. But the adversarial attack perturbs one pixel around the forehead of the cat, and now the neural network thinks it's not a cat, but a deer. So creating this adversarial image is an optimization problem, and basically all the current adversarial attacks created adversarial attacks which exists in the real world are based on optimizing. So how much we do understand about the adversarial images? We know that these adversarial samples are solutions to the complex optimization problem, but that is it about it. So what we understand is the neural network's decision boundary is quite brittle, and in the high dimensional space, which is very sparse, this brittle boundary leaves a lot of space to accommodate these adversarial samples, and the optimization finds the leaks in this decision space, and thus an adversarial image is found. But what we don't understand is why this, how the neural network, how this adversarial images makes the neural network misclassify. And at the same time, we cannot explain the butterfly effect on the activation of the layers by these minimal perturbations. So first, let's understand that how can we understand how a neural network thinks. So we have an image of a cat, and let's see what our neural network thinks it is. The neural network thinks it's a cat. So far, so good. But let's also try to understand the decision of the neural network, that's why the neural network thinks it's a cat. So there are quite a few methods which are which have been developed to understand the decision. One of them is by creating a saliency map, which essentially gives the regions of interest where the neural network is focusing. Essentially, the pixels in the image which are more productive for the neural network for the decision. And when we pass this label back to the neural network, we can generate the saliency map. And this is done by backpropagating the gradients in a different way than changing the weights, but rather than just getting the derivative of the output with respect to input. And when we overlay this saliency map over the original image, we can find the certain areas of interest within that. And another approach is using the gradient weighted class activation maps, which uses the saliency map, but along with it, it also uses the activation which the network has for the given input. And in the same way, using this, we can find the region of interest for the neural networks. So now coming back to the attacks, so we have a adversarial attack. In this case, we have a pixel attack, and we attack the image, and we find an adversarial image. And this adversarial image is classified as a deer by the neural network, and we all know that it's not a deer, and we don't understand that why changing just one pixel has made the network to make a decision it's a deer and not a cat. So what we can do is we can ask the neural network again the same way that why it's a deer, and let's try to understand what's happening. So when we feed this back to the neural network to create the saliency map, we obtain the saliency is around the perturbed region. So it says that the neural network is now focusing on the perturbation instead of any of the other region. But we also have another method, the gradient weighted class activation map, which also says that the distortion is happened towards the perturbed pixel. So it means that the perturbation, the pixel attack has created a perturbation which has shifted the attention of the neural network. And so we can see on the basis of the pixel attack that the original saliency map is now converted, is now focused on the perturbation, and the original activation map is kind of distorted towards the perturbation. But what about the other attacks which are in the wild? Pixel attack was a L0 norm based black box attacks where an optimization was used as an evolutionary strategy. But in this attack, the projected gradient descent attack, the optimization is based on the gradient backpropagation, which is using the stochastic gradient descent. And it's a white box attack. So we know that the adversarial attack manipulates the weights and the activations of the neural network to create this adversarial image. So we can again feed, so this adversarial image is again classified as a deer, but we don't know again why this adversarial image is being classified as a deer. So we can again ask the neural network that why it's a deer by creating the saliency maps and by creating the adversarial map, by creating the activation maps out of it. And then we can also understand in this case also the saliency of the map has changed, and at the same time the activation map is more diffused around the region. And this is one of the reasons why the projected gradient descent attack is able to create those adversarial images. And so here we have the comparison of the two attacks. One is the pixel attack on the bottom left, and another is the projected gradient descent attack, which is on the bottom right. And we can see that these two attacks create the adversarial images in quite different ways, where the pixel attack tries to focus the attention of the neural network around the perturbed pixel or around the perturbation which happens, whereas in the projected gradient descent, the adversarial attack tries to diffuse the attention of the network. But at the same time, why just limit ourselves to the neural network decision when we know that the neural network is based on the probabilistic model? So we can go beyond the decisions of the neural network. And so we also know that the original image is some percentage deer according to the neural network, and the adversarial image is also some percentage cat to the neural network. Although in the original image, the cat, the decision for the cat is more for the neural network. So therefore we classify the original image as a cat, whereas in the adversarial image, the confidence of the neural network is more on the deer. So we know that the adversarial image is being classified as a deer. So we take those max labels. So we choose for the original image the adversarial class, which was the deer. And for the adversarial image, we can choose the original class, which is the true class, which is the cat. And we can apply the same mechanism to create the saliency map and the activation maps of the same. So now this gives us an intuition behind why, how the activation changes between the labels, and is this an effect being exploited by the attacks? So in this we have the pixel attacks saliency maps created, The second column and the fourth column are respected to the true class, which is the cat, whereas the third column and the fifth column images are with respect to the adversarial class, where the adversarial image is being classified as, which was deer. So in this sense, we see a quite common thing, which is that in the adversarial image, the activation map is kind of being retracted around the perturbed region and for the true class, whereas it's being pushed towards the perturbed region for the adversarial class. At the same time, we can also create these maps for projected gradient descent attack, and in this we can clearly see the manipulation of the gradients by the attack, because in the adversarial activation map of for the true class, the activation map is just blown out of the proportion and is focused on very irrelevant part of the images. And so we have several cases of it, and we have a we do a qualitative analysis of it. And in most of the cases, what we found was the pixel in the pixel attack was calling the attention towards the perturbed region, and for the true class, it was trying to retract so that the model cannot attend towards that perturbed pixel for the true class. Whereas in the PGD attack, the effect was focused on the region of interest, where the adversarial attack tries to keep the region of interest intact, but hampers the attention map around the hampers the activation maps for the true class. And so what do we find is that in the saliency map, both pixel attack and PGD distorts the saliency maps for the neural network, but the PGD attack does not create any significant change in the region of interest. It diffuses the saliency for both true and the adversarial class. Whereas in the pixel attack, the saliency is drawn towards the perturbed pixel, which changes the region of interest for the adversarial attack. Whereas for the gradient weighted activation maps, we found that the PGD distorts the activation maps for the true class very much, such that it focuses on the irrelevant part of the images, which was mostly around the corners of the images. And at the same time, the adversarial classes activation maps are being forced towards the region of interest, which tries to keep the overall region of interest for the adversarial image intact compared to the original image. Whereas in the pixel attack, it was trying to do two things, whether it was calling the attention towards the perturbed pixel, where the original perturbed pixel was away from the region of interest, or it was diverting the attention from the perturbed pixel. That means if the pixel was in the region of interest for the perturbed in the region of interest for the original image, it was trying to diffuse the attention maps of the neural network from the perturbed pixel, and this effectively changes the region of interest. But yeah, so in conclusions, the adversarial attacks rely on very different strategies to make the neural network misclassify. Some attacks rely on affecting the activation with the perturbation, while some rely the manipulation of these activations for keeping the region of intact. This opens up the interpretation of the adversarial samples and their effect on the neural network. Moreover, we believe that this insight can help us to understand adversarial samples a bit more. We initially only know that the adversarial attacks changes some of the weights and activations around the for the adversarial image, but we cannot understand like why this was happening or how the adversarial attack manages to do it. And this article shares some insight on it. Thank you, and I'm ready to take some questions if some have any.
We'll leave the questions for later during the debate panel.
Okay.
For the consideration of time, do we have author from the second paper?
Yes. Good afternoon.
Oh,
Hello.
nice. Good afternoon. Maybe for the control of time, I will just remind the authors when it's been 10 minutes past since the presentation starts. Is that okay?
Yes, yes, yes.
Cool. Please share your slides.
Yes. Is my screen visible?
It's not yet visible on my side.
Okay, there is some.
I can share the presentation if you want.
I think there's some problem with the sharing.
Okay, do you want me to present the file you uploaded?
Yes, I have uploaded.
Okay, just a second. Okay.
Oh, yes. Sorry for the inconvenience.
Just tell me to pass the slide.
Yes, thank you. So hi, good afternoon, everybody. I'm Kavya. I'm a doctoral student at University Paris-Saclay. I'm a industrial PhD candidate with Thales Land and Air System France, specifically in air mobility solutions. So I'll be presenting my paper, An Adversarial Attacker for Neural Networks in Regression. Can we go to the next slide? So as Professor Burton in his earlier talk has talked about a lot of standards required to be followed when we are deploying any AI or any system in the industry. So in the last few years, we have seen a lot of increase in the interest of deployment of these AI systems in the industry. We have seen a very good performance on the test data sets and different kind of data set, even also in the generalization of the systems. But still, we have seen that there are certain certification issues. And all the safety engineers, they have to take care of the test performances. They have to talk about all the corner cases where the system will fail, talk about the unboundedness of the system, talk about the boundedness of the input and the output, and where will the system fail apparently. So basically we have to talk about the explainability, trustworthiness, and safe AI in general. So our work in general as a researcher today is to deploy AI with the most certainty that we can have. So yes, next slide please. So robustness and stability in the literature has been defined in a lot of ways. So majorly, there are three ways that we can define. So one is the computational approaches. So in computational approaches, we interact with the network. We attack the network and see how it is performing and what it is giving as a response. And according to that, we try to fool the network. And according to this, we can train the network. So all of this lies under the category of adversarial learning or adversarial machine learning. Secondly, we talk about mathematical proofs. It talks about all the guarantees in terms of Lipschitz constant, in terms of local robustness around the input, in terms of local or global robustness of the network property, and everything comes under this mathematical proofs. And again, robustness as constraints lies in the sense that while we are training a neural network, we will have some constraint on the network, such as hinge regularization, spectral normalization. So these kind of regularization in the literature have been proven to give more robust neural networks and increase the robustness of the neural networks. Next slide, please. So to the scope of the paper, we'll be talking about the computational approaches. So we will talk about the adversarial attacks. So adversarial attacks, I will stress on the fact that these attacks are imperceptible. So perpetually, these are not visible to us. So when we have an image like this, so we add some perturbation E to this according to the value, according to the model structure, model properties. We add some perturbation to the image. Still, it is a panda to us, to a human, but for the model, it is giving something like gibbon here. So a model is getting fooled very easily by just adding some small perturbation to the network. So these kind of problems are not acceptable by safety standards, and this creates a problem while deployment in the industry. So, so these are the threats to the deep neural networks. So next. So, yeah. So adversarial attacks can be divided into 3 categories: white box, gray box, and black box attacks. And there has been a lot of research and a lot of methods to handle these kind of applications for. But all of these attacks, if you'll see, are for classification scenarios. Most of the adversarial machine learning we have seen in the literature talks about image domains, images in computer vision in general. Some literature talk about neural language processing, but all of them talks about them in sense of classification scenarios. So we found there is a lot of gap between between adversarial machine learning and regression, which we will try to bridge using our method. I will talk about it in the next slide. Next slide, please. So I work on air traffic management. So this is one of the application that was presented to us. It is a 4D trajectory prediction that is a prediction of coordinate X, Y, Z and time. So for the case of the case study we have presented in the paper talks about predicting this time. So it is a case of tabular data. As we can see, it is a good example of tabular data because it has both the continuous variables and the categorical variables from the variables 10 to 13. So these are sorted variables. And we have 14 input variables and 1 output variable. So for this, we saw that it is able to have a good testing performance using a fully connected neural network. With ReLU activation functions after each of the hidden layers, we were getting good testing performance, but we have to study how stable and how robust is a neural network. So these are the training samples, validation and test samples as given. So again, the objective of this test case was to predict the estimated time of arrival of a flight. So we see there are two attributes of this test case, that it is a regression problem, and secondly, again, it is a tabular data problem. So both of these things have not dealt in the literature very well. As in the case of tabular data, it is still very difficult to make deep learning work for tabular data. And it has been again and again proven not to be very good for testing performance of the tabular data. Yes, next slide, please. But this tabular data as a whole actually covers a major portion of the data set in the industry. So hence it is important for us to handle these tabular data for deep learning in general and for adversarial machine learning. And as for regression problems, as I talked about earlier, that all the adversarial task, adversarial machine learning, as we have seen in all the papers in literature, that they all talk about it in classification scenarios, because for classification scenario, we can easily define a hard margin around what will be a class. But for regression, there is no natural margin where we can say with surety that it will be an adversarial attack, keeping the changes in the sample imperceptible. So it is difficult to define an adversarial attack, its success, and again, how this adversarial attack can be evaluated properly, how we can define it. So these are the problems problems and gap that we have found in literature, and the kind of application we had from Thales internally. So we had to deal all of them. So for the paper, we have proposed a very simple, novel, and easily implementable adversarial attacker for regression problem for tabular data. We have
There's 1 minute left.
Oh, sorry. Yes, can you next? So we have defined all these 3 evaluation matrices. These are very simple. So this mean accuracy error is the prediction error between what we have, like TXEK is the one that we have after we have added the perturbation and with respect to the ground truth. Fooling error is with respect to what we have without any adversarial attack. And SMAPE is again depending on both the ground truth and the predicted values. So I will stress that it is very simple and it can be used for any data domain and any class of neural network where we can find a Jacobian of the network. And for, like I have said, that we have been using tabular data. So with using our attacker, we can attack only few of the input features. So you can attack just few of the input features so that you can study the sensitivity of the input and see how it is affecting the performance of your neural network or not. So we have observed in our applications that categorical variables don't contribute much to the attacking of the neural network. So and have very less effect on the performances, but it has effect on the performance of the neural network. But we can remove it while having an attack on the neural network. So yeah, and we have presented our results on this real data set from Thales. And how much time is left?
Time's almost up. Please quickly wrap up if you can.
Yes, so T is a neural network and TX plus E is the attacked output after we have attacked the neural network. Next, please. So in mathematical terms, it is this optimization problem that you can see. And it is from this convex set of C. And we have solved it using this linearization, and we have to just find a Jacobian of the neural network. And yeah, and it simplifies to a very subordinate norm of this problem. Next. So these are the results that we have found. We have compared with 3 random noise attackers, and we always found that we were able to attack the network and it performs better than all the 3 random noise attackers. And as I talked about spectronormalization, we also saw that these when we have a model trained with spectronormalization, these attackers were not as successful as that. And this proves a theory that spectronormalization makes the system more robust. Yes, and with this attacker, we were sure that we will attack, and because it always calculates the worst attack. And since we're talking about regression problems, so L1, L2, and L infinity are the most used norms on input and output, and all of these are used in different kind of applications. So we have proven that our network works for all of these 3 norms. Next. So again, the conclusion is that we try to bridge a gap between adversarial machine learning regression task and tabular data. It is a very easy implementable Jacobian based adversarial attacker. And thus it will help us to explain AI more for the safety engineers to define tasks and make the system more robust. So yeah, thank you.
Thanks for sharing, Kavya. Similar with the previous paper, we'll leave the questions for the panel session later. Yeah. We have the author from the 3rd paper.
Yes, I'm here.
Can you share? Do you have any?
Yeah. Can you see my screen?
Yes. I'll also start counting the time now, and I'll remind you when it's 1 minute left.
Okay. So good morning. I'm Seán Ó from Cedar Ireland Center for Applied AI, University College Dublin. My co-authors are Suruchi Gupta and Michael Madden from National University of Ireland, Galway. I'm going to present our paper, Coyote, a data set of challenging scenarios in visual perception for autonomous vehicles. As a standard outline, introduction, motivation, related works, Coyote data sets, and some experiments that we did and what we concluded from it will be given in the end. Recent advancement in technology, both hardware and software, led to advancement in the fully autonomous vehicle by taking them closer to level 5 with each passing day. Honda Motor recently announced level 3 driving vehicle. Tesla is at level 2, Mercedes, Ford, and others are planning to launch later this year. These autonomous vehicles use a combination of sensors such as LiDAR, radar, cameras to observe the surrounding. The video stream from the camera is synthesized using computer vision technique and machine learning to make informed driving decisions. Here is an example of Tesla autopilot vision system. The right side of the images show what the system looks or how it detects objects in the scene, in the images or videos. As the previous presenters have showed that computer vision, machine learning, or adversarial attacks, how they work or how they affect the machine learning algorithms. Research also showed that it is easy to attack and fool or misclassify objects in an image, which can be an issue in a safety critical application. Beside the success in computer vision and machine learning, that can create issues in situation like autonomous vehicle to human safety. To train these models, there are multiple data sets for computer vision models training. Similarly, nowadays, there are some data sets specifically introduced against anomalies or adversarial attacks, like, for example, fish escapes, which can place anomalous objects in front of the vehicle in the image, or Wildash considered natural risk in images like distortion, overexposure, windscreen, or adverse condition data set with correspondences that contain images with fog, nighttime, rain, and snow situation for semantic segmentation. All these categories result in a case or scenario where the view is not clear and many objects are hardly visible for the algorithm to detect. In our work, we are not concerned with adversarial attacks through image modification, as the previous presenter mentioned, but with problem arising from edge cases that might not be all well covered in the training sets, but that will occur in the real world. However, these can potentially act as adversarial examples for autonomous vehicle. We want to use it as a testing set, this data set. We want to use it as a testing set for evaluating the performance of the state-of-the-art object detection model to identify the challenges scenarios for the autonomous vehicle and suggest mitigation for those models. So Coyote data set, the name Coyote comes from the cartoon we used to watch in childhood, where a roadrunner and a coyote runs after each other, and the roadrunner passes through a tunnel, but the coyote hit the wall, the mountain or the wall. Many of you might have watched it. The data set contains 7 broad categories that results in 894 images. 6 of them are for object detection and 1 is for semantic segmentation. All of the images are in JPEG format and publicly available unedited images. I will rush past through the examples. These are some samples from the Coyote data set for art in surrounding and murals. So these are the samples where we collected that what will an autonomous vehicle do when they see such images on the road or beside the road. These are from vehicle art and texture, like if this is driving on a road, what it will do. On road scenarios, animals or birds are completely snowy roads, what it will do, or billboards on the signboard. Street signs modified by artists or kids or some specific design specific to countries. parking spaces, for example, images showing presence of unseen object on parking space or non-standard signs and warnings to the drivers. Some advanced scenarios where, like, for example, if you change the color of the center line with the side lines, that completely change the meaning, because yellow line is the where you don't have for the parking, and white is the in the middle normally, that shows whether to overtake or not, or the barcode that can give some other messages instead of the pedestrian crossing. And finally, the seventh category for the 3D illusion, which was specifically selected for semantic segmentation. We selected 19 images for semantic segmentation to understand the impact of 3D illusion on self-driving applications. So this is the data set samples that comprise of Coyote data set. To test this data set over benchmark models, we selected YOLO v3 and Faster RCNN for object detection, and Deep Lab v3 for semantic segmentation. And these models are pre-trained on MS COCO data set. And we also took MS COCO validation set, as well as random subset of Kitty data set validation set to compare our results with them. Here you can see results from the YOLO v3. On the left shows some cases where YOLO v3 performs correctly. The model distinguishes between the billboard and the person with confidence of 99%. It identifies the car decorated with fruit, and the altered stop sign bottom left with confidence values of 87 and 95%. That was good. However, on the right are the images where YOLO failed. A person like sculpture, which is not really a person, is mounted on a bicycle, and the model identified it as a person with 95% confidence. Additionally, the murals in the center right and bottom right images are identified as real objects. Similarly, for Faster RCNN, here you can see the successful identification of a bicycle mounted on the front of a bus. The top right and bottom right images show the instances where a YOLO v3 fails, but Faster RCNN successfully identified the stop sign and the grass texture car. The bottom left image shows that the mural with a cyclist does not confuse the model. On the right, you can see the top left and center left images where Faster RCNN identified the objects from billboard and murals as real with high confidence, 98% and 99%. The bottom right image shows a sculpture made from a discarded street sign, but the model identified same as actual stop signs and misclassified the arrows as a parking meter with 90% confidence. In terms of semantic segmentation for 3D illusion, a Deep Lab v3 correctly segment the people in the first image as is not affected by the art. In the bottom figure, people are standing beside a painting of a bicycle and road with a tearing illusion. The model classified the cyclist and the bicycle as real, along with the real people standing beside them. The most common failure is this in semantic segmentation are in classifying art as real objects. This can make the, I would say, autonomous vehicles susceptible to failure in presence of 3D illusions. To show the overall performance, Faster RCNN shows good result for many images in the Microsoft COCO and Kitty dataset, but shows poor performance on the Coyote dataset. The number of true positive for Faster RCNN is significantly higher than that of YOLO v3, leading to fewer false negatives. However, Faster RCNN has a very high number of false positive, which reduces the model overall performance. Hence, its accuracy is very low at 52% and precision is 60%, where its F1 score is 68%. As a whole, when we see the results individually as a per class or overall, we saw that the Coyote dataset affect the performance of both Faster RCNN and YOLO v3 models. In conclusion, we introduced a new testing data set. We found that the painting in art and surrounding and murals category confused the model the most. In advanced scenarios or 3D illusion on art on the road, Deep Lab v3 can correctly segment humans on the background, but it fails in some cases when 3D representation of objects are painted all walls. Analyzing the aggregate result for both models show that the faster RCNN model captures more details than the YOLO V3 model. This helps the faster RCNN model make better inference. However, it also makes its model more vulnerable to failure or from edge cases. The key risk associated with the kind of errors we identify in this work is that a vehicle may react inappropriately, for example, braking sharply to avoid hitting a person that is actually an image on the back of a van, or preparing to drive ahead when the street ahead is actually a mural. However, sensor fusion, common sense reasoning, better treatment of scale, and spatial-temporal reasoning can mitigate the risk. As a future direction, we would like to extend the data set by adding new images to the same categories from within vehicle, as well as adding new categories, and to do in-depth annotation of these models, and add additional sensors information into it to have a fusion instead of just one form of data in it. Thank you so much. If you have any question, I thank you. Thank you so much.
Thank you so much for sharing it. It has Iksan. Isan. Okay.
Yeah.
All right. Now we'll get into the debate panel session. Consider that many presentations previously overrun by a few minutes. I think we will need to shorten our debate panel. So we will still end our panel at 1:50 p.m. just to save more time for later sessions. All right. So if people have any questions regarding the paper we just presented, feel free to raise your hands. Florian, feel free to raise your questions.
Yes, hello, this is Florian. I have a question to Isan. So thank you very much for this talk. Very, very exciting and very visually interesting. I was wondering, do you have any suggestion how to overcome these confusions, for example, on murals? Because it seems to me that this is actually not a problem of the object detection network itself. It seems like it's doing what it's supposed to do, just that the overall context needs to be understood. So do you have an idea how to eventually handle this problem?
One thing I will say is to just to clarify, we didn't train the model with this data set. We just tested the existing models that are trained on normal images with these images. So a possibility is to extend this data set and then train it or add such images in the real data set so that the model are trained on both type of images. So that's one solution. And yes, the second one is that to use fusion of sensors. Like normally, if it is, we consider autonomous vehicles, they will be using multiple sensors. So other form of data might help them in taking the decision. But our objective is to reduce the confusion or ambiguity because a small pixel change as being shown in the adversarial attack, that one pixel change can change the whole result or classification. So that's why we are trying to focus on these edge cases, that we should focus on these as well.
I see. Yeah, maybe a combination of semantic segmentation and object detection could also help.
Yes.
To carve out the context here. Yeah. Okay.
Agree.
Thank you very much.
Thank you so much.
Great. Jose, do you want to state your question?
Yeah, I had a question for Katya about the regression problems. And well, it was basically at the end when you introduce the metrics for evaluating how well the perturbation goes. I assume that this is well explained in the paper, but maybe I think that my first question was, okay, how are you going to balance the degree of perturbation with the degree of change in the output? Because in classification, you only want to change the class, but here you want to just to have as much as changing the output as possible, because it's a regression problem. And it seems that you have sorted this out by saying, okay, I want to maximize how much I can change the output, put in some kind of maximum level on the perturbation.
Yes.
But if you were to look for a trade-off, do you have any idea, because the output has a magnitude, maybe it has a different distribution for each problem? So do you have any idea where we could say, okay, how can I balance the perturbation that I put and the change in the output?
So firstly, that whatever perturbation we are generating, it is based on a parameter. As I said, like it's a delta parameter, which is trying to introduce the maximum perturbation. So what we say in the paper is that we try to generate the worst attack. That is the worst attack. So using that delta, with that parameter delta, it will be the maximum deviation we can get on that sample with that delta. So that is the maximum variation you can get on that sample. So that is the limit of the maximum deviation that you can have on the ground truth or the prediction performance of the network.
Yeah, but that's I think that's the first approach. But for instance, if you are predicting, for instance, sales or something like that, which is just a number. So maybe you are interested in knowing, okay, maybe what if I can get 20 points of underestimation or 20 points of overestimation? It's not the same. It depends on the problem or not. Yes. So sometimes maybe you can get 100 overestimation, but with that perturbation, you can only get 1 units of underestimation. So I think that depending on the problem, maybe there's some other metrics you could investigate about how to balance these two things.
Yes, we have not tried that, but we can try to add more parameters to the constraints that we are putting on the optimization problem. For us, it is just the perturbation, maximum perturbation, that our perturbation should lie within this ball on the input. So this is the parameter we have for optimizing for now.
Okay, thank you. Just as a suggestion, maybe you could look at regression error curves, because that makes a connection between regression and classification in terms of you put a level and you say, okay, I accept some kind of error on the output.
Yes.
And that's a good way of just depending on how much error you allow on the output, you can connect that with the classification problem. So I think that could be an interesting connection to see how all of these metrics in classification, you can just connect them to your metrics in regression.
Yes. Okay. Thank you.
Yeah. Actually, I have a question. A couple of questions for maybe a simpler one for Kavya. Is the data set that you're using available?
No, it's internal, so yeah, we can share it.
Okay.
Yeah.
I would be very interested in and also understanding how, if I understand this correctly, I mean, you're applying now you're thinking about applying neural networks to do 4D trajectory prediction, right?
Yes, ultimately, yes. So again, I
how,
would say that this regression problem, for now, we are just predicting just one, but it can be applied to any number of output variables. So it can predict multiple number of output. It can generate adversarial attacks. I mean, we have tried for multiple outputs as well. So even if we are predicting 4D trajectory also, so it will work for that too.
And I mean, are you getting really improvements, let's say, with respect to maybe you're comparing this to BADA, right? Maybe the BADA system for 4D trajectory prediction.
No.
And I was wondering if you're really, if there's a good hypothesis for, yes, we should maybe start moving towards, neural networks for these kinds of problems. And now we have to worry about, of course, adversarial attacks or the robustness in general, right? Of this approach.
Yes. No, we have not compared with BADA or any industrial standards, I guess. So, but yeah, this is one of the things that we would like to in future to compare with.
Yeah, and I was also interested in the fact that I mean, there are not many, this tabular kind of data sets.
Yes,
I mean, there are not many, and you applied L1 norm. I mean, and
yes, we applied
we've
one
noticed that
norm.
L1 norm does not really work well with this.
We applied L2 norm, L1 norm, L infinity norm. So we have tried to use it for different kind of norms, because I understand for regression, all these three kind of norm work differently, and we should have a bigger pool of norms that we can have on both input and output. So we can have combination of L1 and L2 on input and output, L2, L2, L1, L2, L infinity, infinity. And so we can have number of combinations that we can have on the norms. So yeah.
Yeah, I think for L2 and L infinity, I can see sort of how they are an expression of the distance, right, of your adversarial example.
Yes.
But for L1, it's a bit fuzzy.
Yes, so for whatever we have explained in the paper, so there are subordinate norm, because a problem simplifies to calculating a subordinate norm of P and Q. So whatever combinations we can calculate. So we can have different combinations of P and Q and calculate for 1 and infinity, infinity, infinity. So yeah, in paper, like when we are talking about L1 attack, it means that we have L1 norm on both the input and output. Again, L2 is both 2 on input and output. We have not given results for mixed norms, but it is wherever it can be defined, we can easily calculate it in terms of subordinate norms.
Yeah. And yeah, okay, thank you. And I have one question for Aysen, where I thought that was really a creative approach to testing these classifiers. But if going back to the let's say to the certification framework, right? So maybe you want to prove that you're testing your classifiers or your neural networks at the edges of the distribution, right? So have you thought about how to characterize the likelihood of the coyote data set? Because I mean, if you're just coming up with all these creative examples, right? I mean, you can always come up with new ones, right? So when would you be done? And this is where that yesterday there was a conversation about characterizing a domain, right? So and ideally your adversarial example should be somewhat within the domain, right? So that to make your testing relevant. Do you have any comment on that?
You are right. Like I agree. Like some of the images that I have shown even are not from the autonomous vehicle or the camera view from a car perspective. They are like from a road or from not the horizontal view. So what we were trying to do in this, I totally agree that we should be in the domain, but it is something we would wanted to highlight that there are some scenarios. So if a machine learning algorithm can be fooled by one pixel change, what if somebody changed the footpath to a barcode? Or what if somebody changed the color of the road, the marking on it from white to yellow? What will the reaction of the autonomous vehicle be? So it's like we are trying to just initiate this conversation. So currently our point of view was that. So, but yes, we need to increase the images. Like ImageNet is 1.5 million and we have only 1,000 images. So there is a big work to do. Yeah. But it is something we need to focus because there is a human factor involved in it, and even one human loss is a big thing, and that can damage the whole industry as well. So
yeah, I think and there's currently in the US, I mean, people are starting to think more about how to make these systems truly more robust, and there's a lot of talk about third wave AI, sort of how you introduce sort of symbolic reasoning. Right, how you combine symbolic reasoning with this neural networks, right, with this connectionist approaches to AI. And if you had, that kind of foundation, right, to your solutions, you will not be fooled as easily, because so machines will have a better understanding of what's going on. So it doesn't make sense to see a tiger here in the middle of the street or something like that, right? No, yeah, I mean, I think this is a good starting point, yeah, for that, yeah, for a new approach to thinking about also the solutions.
It's like a testing, like, okay, let's just check. It's provide state-of-the-art result on the benchmark data set, but can it provide some benchmark or state-of-the-art on this specific anomalous or testing validation set? So it's what our objective was, not to keep it as for training, but just as a testing set, and see how well the models that are providing state-of-the-art, will they do the same on this data set. So that's like some sort of certification, as you mentioned.
I am aware of time, so maybe we can just take Jose's last question, if you can make it quick.
My question was actually for Shashank. Shashank had his hand raised, so maybe you can talk first. And you wanted to ask a question.
Yeah. So I wanted to ask a question to Kavya. Like in my image classification domain where I worked with, I noticed that when we have an adversarial attack and there have been proposals to adversarial defenses. So what happens is when we have an adversarial attack, like an infinite attack, and an adversarial defense to counter it, and we have a defense which can effectively counter the infinite attack, but the model still remains vulnerable to other norms of attack like L2 and L1 and L0 norms of attack. So what the community has been trying to do is like they are trying to mix up the attacks using like a combination of either L0 L infinite or L2 L infinite and so on and so forth. So have you tried a combination of those attacks in the regression domain to understand, like, is that problem which is in the classification is also in the regression?
Oh, yes. I mean, this is the paper where we are just introducing the generation of adversarial attack. We have been learning now with those adversarial attack to do the adversarial learning and understand these attacks. If we are adding these attacks as a data to the data set to learn the neural networks, how it will perform. So yes, there is always a problem where, I mean, it will be better to learn a network with a combination or ensemble of these kind of attacks. So it will make the network more robust and improve the performance of the network. So yeah, it's the same for the tabular data as well, for the regression problems, I would say. So yeah, we have been trying to have an ensemble of all of these attacks. So yeah. I think this was.
Thank you.
Okay. Yeah, welcome.
Jose, do you want to raise your last question?
Well, it was just a question about the understanding that you are doing, Shashank, with the attention maps. How do you plan to use it in practice to prevent some of these attacks? Or do you think that there might be some kind of attack that is designed not to modify the attention maps? Do you think that's possible in some way?
Well, it's still quite far-fetched because we still don't understand that how still, like, we know that they are changing the attention maps and they use different strategies to change, but we still don't understand like how those perturbations change it. So probably some development in more in the explainability of the AI would help the research to understand that why those adversarial attacks exist in one place and how they can be better be like how can we develop more robust defenses. But the current article, the scope is just to understand that, to open it to the community that the adversarial attacks don't use just one strategy to change misclassify. They employ different strategies, and they can vary a lot depending on which optimization you use. So it's still quite, I would say, far from using as a method to make models more robust. I hope I answered that.
Yeah. Yeah, I think that's a part of fundamental and these actually adversarial attacks, all of these area is started as a motivation to understand how neural networks work, and not in many cases not as real examples you can face, as for instance this new data set in this domain has been presented where you can have more realistic images that you can see. But I think we need all of this to understand how deep, especially deep neural networks work. And other techniques, I think that some other people say this kind of using tabular data today. I think that was also very interesting because it's not just images or audio or text. There's still a lot to do with tabular data.